Hello and welcome everybody to this AAMP extension. This extension is, or I'm recording this extension because today we had a problem in the lecture. Unfortunately, two-thirds of the lecture were without sound. Not during the lecture, I didn't notice, but when I checked the recording, I found out that we don't have sound. So in order to compensate at least a little bit, I'm going to cover the most complicated part, I think, at least what was the most complicated part today. That's the Frank-Condon approximation. Everything else can be understood from the slides, I hope. But let's go through the Frank-Condon principle one more time, especially when talking about bound and unbound states. For this, I will share my screen with you. And switch to PowerPoint. Okay, so the spectroscopy of diatomic molecules, and we reached the Frank-Condon principle. The Frank-Condon principle comes into play when we're dealing with rho vibronic transition, which is this fancy word, electronic, vibrational, and rotational transition in one go. So we have a transition between one potential energy surface and some other potential energy surface. In each of these potential energy surfaces, we have some vibrational levels. And for each vibrational level, we have again a variation with respect to the quantum number of rotation, here denoted as J. Okay, so if we can assume, or if we go back a few slides in our mind, we started with the Born-Oppenheimer approach in order to actually address a molecule in a stepwise way. We said we solve the electronic problem and then we deal with the nuclear part of the wave function. So the electronic part was the difficult one. We introduced the Hartree-Fock approximation. This is how we get the potential energy surface. If we have the potential energy surface, and for example, for a diatomic molecule, this surface is one-dimensional because we have only one coordinate, the distance between the two atoms as our coordinate, then we have these curves. And solving the nuclear part of the Schrödinger equation is simply solving a particle in a one-dimensional potential. So we can use some techniques to solve these problems, like discretization, turning the differential operator into finite differences for the second derivative, and then solve this differential equation of second order in order to get our energies and eigenstates. Now we have the vibrational energies, and then we have the rotational energy sitting on top, because there is also energy in the rotation. In total, the wave function can then be split into a product having electronic, vibrational, and rotational contributions. And when interested in the interaction with photons, so if you want to know about adsorption spectra or fluorescence spectra and so on, we typically have a bunch of selection rules which are related to symmetry features and to the conservation of the spin of the interacting particle, or let's say this way, some conservation numbers. Typically, it is the spin, for example, of the photon. As a boson, spin is 1, and therefore we have this angular momentum conservation before and after the interaction, and this led to this delta L plus minus 1 for excitations, and in the rotation it leads to delta J plus minus 1. And so in the case of a transition from a ground state to some excited state, we can't give clear selection rules anymore, and instead comes this Frank-Condon principle into play. And it tells us that the total wave function when split up in this, has this electronic vibrational rotational part. And if you would like to know the probability for a transition, an excitation from one potential surface to some other potential energy surface, then we simply need the nuclear wave function in the upper and the lower state, and then we integrate over the product and take the square of this. So we integrate along, for example, in a diatomic molecule, it's a potential energy curve. So it's just one dimensional. We integrate over the R, with R denoting the internuclear distance. And what are we integrating? The product of the two nuclear wave functions in the upper and the lower potential. Then absolute square gives us the transition probability and is therefore proportional to the intensity of our spectrum for this transition. Now, these are three examples. You can see that the actual position of the equilibrium distance in the upper and the lower potential has an effect on the overlap of the nuclear wave functions. In case A, we have two states which are having the same equilibrium distance, and therefore in this case we have good overlap for vibrational states of the same vibrational quantum number. So here it is 0 and here it is 0. So this would give best overlap. But for example, for nu equals 1, the nu equals 1 in the upper level would have the perfect overlap. Note that here it is actually the probability, so the squared wave function, which is drawn in the picture. But for the Frank-Quantum principle, you have the product of the wave functions. And then you integrate over R to get the corresponding value. You square it, you get the intensity. Now in case B, we see the excited state is a little shifted to the left with this equilibrium. This means that this is probably an excitation where electrons are now more located between the two atoms and therefore are compensating the repulsion between the two atoms. Therefore, the molecule is a little bit compressed, or at least a little bit smaller. This would be an excitation where you remove electron density probably from the between or along the internuclear distance. Therefore, the molecule opens up and we have an equilibrium at slightly larger distance. In these cases where the equilibrium distances are not coinciding, we have a different overlap pattern, because in this case, for example, the vibrational ground state here will have more overlap with higher vibrational excitations in the upper potential, simply because here the overlap is then better at the turning point of the nuclear wave function in the upper potential. So we can see the equilibrium distance relative to each other in the upper and the lower state affects the structure of my vibrational transitions, or my bands, which I can find. Remember, we had the bands. This is all the possible combinations of vibrational quantum numbers between two electronic states. This gives me a system of bands. If I pick one combination, for example, nu equals 2 in the lower potential energy surface to nu equals 5 in the upper. So this would be a transition that I'm looking at that gives me some band structure. This is the band, and if I have sufficient resolution, I can see in the band the actual rotational lines. Now, these band systems, they can have a certain structure depending on the equilibrium positions in the upper and the lower potential. As you can see here, we distinguish between grouped spectra or row spectra. So row spectra for different equilibrium distances. And knowing now about this Frank-Quantum principle, we can also understand this feature of absorption and fluorescence in lasers, which I covered in one of the earlier lectures, where you could see that absorption happens at higher energy than fluorescence, and this can be seen in the Frank-Quantum pictures and understood as follows. You have a molecule in some vibrational ground state, in some electronic ground state. Then you excite, and you have better overlap with vibrationally excited states in the upper potential. Then you have radiationless relaxation here, and at some point you have good overlap of this nuclear wave function with a nuclear wave function that corresponds to a higher vibrational quantum number in the ground state. But if you look at the excitation here and the relaxation here, this is a much shorter arrow, meaning that the relaxation here from one electronic excited state to the electronic ground state is a process that has a smaller delta E. Therefore, the fluorescence spectrum is typically shifted to lower energies. And if I have new bars, so the wave number in this direction, meaning that the fluorescence spectrum will be somewhere here at lower energies. Another thing we can understand is photodissociation. Photodissociation is only possible in combination with an electronic excitation. Why? Because if you look at the nuclear wave function in the ground state, so this is the electronic ground state, for example, and you are in the vibrational ground state, and if you compare this to some nuclear wave function in a vibrationally excited state, where I'm even above the dissociation energy, so this continuous state, if I look from here to here, this arrow would be a transition where I'm changing my momentum immediately, right? Because here I'm having a lot of kinetic energy in the motion of the nuclei in one go. So that's not possible. And if I go from here to here, where I would have some overlap, I have the problem that I have completely different core locations. So the core would have to locate spontaneously. It's also not possible. So in general, within the same potential energy surface, I cannot have photodissociation because there's simply no good Frank-Compton overlap. However, if a second electronic state comes into play, it is possible because here I can excite easily if I have good Frank-Compton overlap between the vibrational ground state here and some vibrationally excited state in the electronically excited state, and have a state occupied which is no longer bound. Then the molecule will dissociate. So this is photodissociation. And then another thing we can understand is optical predissociation. In some cases, you might have electronically excited states that are that have similar energies, right? So they're in the similar energy regime and have a crossing somewhere. So this is always is a hint that there is something going on between a coupling of electronic states and vibrational states. Here we have the a feature which is called predissociation, happening in cases where we have a vibrationally excited state in the state AB. And if you compare this with the electronic state AB star, this state can have some vibration, some Frank-Compton overlap with my nuclear wave function in the potential AB, so that we can relax and occupy a vibrational state in AB star, meaning that a nuclear wave function in the state AB star, here this line, has, for example, a certain structure. So this nuclear wave function has a certain shape, and it has good overlap with the nuclear wave function of AB of this vibrationally excited state in my potential AB. And in this case, we have this coupling. It is possible that the wave function, the electronic wave function, changes. So we go from AB to AB star, and at the same time, we also change the nuclear wave function without the change in energy. However, in this configuration where now electronic energy is reduced because we're in this AB star, electronic energy is up. We are in this excited state AB star, but we have reduced vibrational energy. So instead of being here, for example, we're at the nu equals 17, we are at the nu equal 12. But in this AB star, this vibrational state is already a state which is no longer bound, and the molecule can dissociate, right? So we have just shifted energy from electronic to vibrational, but in this new electronic potential of this new excited state, you have a vibrational state which is no longer bound, and then the molecule dissociates. And this is called the predissociation, because actually the molecule is still bound if it's in the electronic state AB. The analogy in the atom, where we only have 1 degree of freedom, namely the electronic excitation, is the autoionization. Autoionization is if I have, for example, an excitation, electronic excitation where 2 electrons are occupying different orbitals. So it is a state characterized or different from the ground state by having 2 electrons at different orbitals. And in principle, this energy for the excitation of both electrons is already high enough to kick 1 electron out. And in this case, the atom can relax by sending out 1 electron. So this is the in principle the same concept. You have enough energy for a dissociation, in this case, an ionization of an electron. So there is a relaxation going on. You can think of one electron being going back in its ground state orbital, and this energy is used to kick out the other electron, and you have an auto-ionization of this atom in this case. So this is the analogy. And then finally, this is the point that is very hard to understand without reading the book, simply from the slide. So this is the most important topic to be covered in this extension. It is the bound to non-bound transition. So we have a molecule, it is a linear molecule. We have 1 degree of freedom, a diatomic energy only a function of the distance. We have 2 potential energy surfaces. One is this one, the excited state, and one is this, the ground state, for example. Now, let's assume we are in the excited state and we have some vibrational excitation, which is described by nu prime equals 7. Here, the hint in spectroscopy, for whatever reason, the excited state is typically singly primed, and the ground state has this double prime indicator, double prime superscript. Okay, so we are in the electronically excited state, and nu prime is 7, so we are also vibrationally excited, and this is the corresponding nuclear wave function. Now, how do we apply the Frank-Compton principle here? We do exactly the same thing. We only have to take into consideration that there is also nuclear motion involved in these non-bound states, and we have to do following. So we calculate a so-called differential potential U of R, which is simply the potential U, the potential E double prime pot of R, so the potential energy surface in this lower state, plus, and what I'm adding is simply the kinetic energy, which I have in the vibrationally excited state in the upper potential. Obviously, at the turning points here and here, I do not have kinetic energy because this is when the motion turns around and there's the velocity is 0 for a moment, but the velocity is at maximum here in the middle. And this energy, which is the difference from this actual energy to the potential, this is what I add to the lower potential. And what I obtain is this dashed line, which I'm following now with the mouse. Right? Where's my mouse? Here it is. I'm following here with the mouse. Right? So this potential is U of R, the differential potential. Why do I need this? I need it for the following reason. The energy, so the position of the spectral line is determined by the energy difference from here to here. So this is the difference. This gives me my energy. But for my intensity, I need now the overlap of the wave functions, this wave function and this wave function. Now, what is this wave function? This is an loosely bound or an unbound state. So this means that one atom is just coming in and leaving the other one. And the approximation we can do is via Airy functions, which are solutions of the Schrödinger equation given a linear potential, because here this is all what matters. We can approximate the potential here as a linear potential in this region, and we get these functions. Now I'm calculating these functions for all possible energies in the energy regime that I'm interested in. And in order to get the transition probability, however, I'm only looking at the Frank-Compton overlap integral in the regime along, where is my mouse? This is so weird with WebEx. In the regime where this energy that I'm interested in, so I'm interested in the probability or the intensity of the spectral line in this energy region. Where is it cutting my differential function U of R? And at this area where it is cutting, I have to compare the two wave functions. So the Airy wave function of the not bound state and the nuclear wave function of the bound state. I integrate over this area and I get a value. This is the value that is, if I take the absolute square, proportional to the intensity. Now, since any state here is possible, this is continuous because we are no longer bound here. So we are in the continuum regime here. The spectrum is obviously also a continuous spectrum, but it has some wiggles because at some point the Airy function has good overlap with some wiggle of my bound state and sometimes not. Now let's see what we obtain here on the right hand side. This is an example spectrum where we at first have a bound to bound transition. So in this high energy regime, we are discrete. We have a discrete with discrete absorptions, for example, in our spectrum. And then if I have energies which don't go from bound to bound, but from bound to not bound, which means that we have less energy, we're in the regime of long wavelength or less energy, we have a continuous spectrum, but it's also modulated. And the modulation comes from the overlap of the Airy function with my nuclear wave function in the bound state. And the fancy thing is that by pulling the Airy function along or calculating the Airy function for all these energies and looking at the overlap, you can see that it's basically probing the nuclear wave function of the upper state. And so the number of peaks in this continuous spectrum here is related to the number of wiggles in my state, my nuclear wave function of the electronically excited state. So this is the number of these peaks is related to my quantum number mu prime. So you can see even for these cases here where I have a bound-unbound transition, I can use this Frank-Condon principle. Again, we don't have clear selection rules, but we can use the overlap of the nuclear wave function to get an expression which tells us the intensity of a line in emission or in absorption between states, which we call rho vibronic, so states involving electronic excitation, vibration, and rotation.